Good morning, everyone. Yesterday, Kate talked about what we're using the ANCSA samples for in terms of characterizing the volatile species and where they are within the samples, and if frozen curation helped to improve their retention in the regolith. And at the same time as we've been doing that study, we've also been evaluating space weathering features throughout the sample as well. So that's what I wanted to share. So essentially, we've been doing a comparative analysis of the permanently shaded, partially shaded, and fully exposed soils using TEM, EDS, and EELS. I'll be largely sharing some EDS data. And the goal, kind of the broad goal, is to improve our understanding of how solar wind irradiation and micrometeorite bombardment work together, and separately to form these space weathering features. And this study was also kind of more of an open-ended study, taking a lot of images of a lot of different grains and starting to see if trends start making themselves known, and we can infer process from those trends. We've looked at 17 TEM grids of microtome samples so far of the samples, and 7 fib sections. So we should probably make some more fib sections, but the microtome samples, time really dilates when you look at them because there's so much material on the grid, and we could analyze them for long periods of time. So continuing forward, we want to prepare some additional fib samples from the exposed samples because we've kind of neglected those. And we also plan to look at additional frozen samples. But at some point, we will have to make a judgment call on if we've looked at enough samples and start to take a look at the massive amount of data that we've collected and see what sorts of questions those data answer and what sorts of conclusions we can make from them. As we're going through the samples, the aspects that we're trying to consider are how the rim's characteristics vary as a function of mineral species, and also if there's a relationship between the recent exposure history, because we're looking at those samples from underneath those boulders, and the abundance / characteristics of the rims that we find. And so when I say characterize, we're specifically looking at what the mineralogy is that we observe and the glasses, and characteristics of the space weathered rims, such as their thickness, the host material that they're on, their contents, and those contents can be single component or multi-component vesicles, nanophase iron particles, vapor deposits, melt splashes, sputter deposits. And then also attempting to characterize the size, abundance, and distribution of those rim contents. So seeing if we see more vesicles or more iron particles on different phases. So that's a bit more of a difficult granular question, but those are things that we're keeping in mind. So yesterday we talked about volatiles, and those are definitely things that were characterized through the samples. I'll talk about some exposure differences, vapor deposits, melt features, and vesicles. And please keep in mind that these features that we're seeing so far, we're still kind of in the qualitative phase. So I'm going to share kind of trends that we see, common things that we encounter, what they look like, and why they could be important. So I'll start off with the perhaps lackluster results so far. In terms of the recent exposure history, do we see differences at the nanoscale in the mineral phases? There's plenty of evidence to suggest that we would see such features. There's space weathering associated optical characteristics that say that permanently shaded samples or partially shaded samples should have fewer space weathering indicators. But at the scale that we're looking at, we're just really not able to tease out any differences. We're seeing in the shaded samples, we're seeing vesicles, implanted volatiles, rim thicknesses that don't seem to vary in any systematic way. So at this point, we can't really, we say with any confidence that we're seeing differences in the exposure, and that could be a function of the exposure time and the mixing of the soil components, but that's just not something that we're seeing so far. So to move on to some of the kind of space weathering themes of stuff that we've looked at, we're going to go through several TEM. These are dark field HADF images on the left here, and this is an EDS elemental map plotting iron, magnesium, aluminum. So a vapor deposit or a sputter deposit feature that we come across pretty frequently are ferromagnesian deposits on plagioclase. Plagioclase itself seems to be rather featureless and more of a substrate for deposits are found on. Plagioclase doesn't typically that we see accumulate vesicles or amorphous rims that we really see. We do see a lot of depositional features on it though. And one of them is a rim of iron nanoparticles and also magnesium, and they very typically often go together in this way. Here's another couple of examples of calcium plagioclase grains with coatings of nanophase metallic iron particles with magnesium alongside with them. And so what we're kind of interpreting this is adjacent particles that would be ferromagnesian, pyroxenes, olivines that are the materials being transferred in some way, and the iron nanoparticles are nucleating and growing in situ to form these rims. Here's another nice example of a calcium plagioclase grain. This one, I'm also showing an oxygen map. We can also see that the iron and magnesium are also correlating with an excess of oxygen. And so we're also getting movement of oxygen, and these are again ferromagnesian mineral components. A vapor deposit variety that we don't encounter often, and which is surprising given the amount of plagioclase in this sub 45 micron size fraction, we don't see a lot of calcium and aluminum silica deposits. Likewise on the ferromagnesian minerals. Here's an example of an olivine grain. This one has some spherical vesicles containing calcium, aluminum, and silica. And here's another couple of examples of olivine grains that have experienced space weathering, and there are sputter deposits of aluminum and calcium. And here, this one looks more like a melt deposit, just in the morphology. But yeah, we do encounter these less commonly. Something we don't encounter, at least to my knowledge, in the hundreds of areas that we've looked, are titanium-bearing vapor deposits or melt splashes. This might have something to do with the relative both abundance and robustness of the oxide phases. Ilmenite, however, on the other hand, will have deposits of exogenous materials, silica, magnesium, aluminum. Here are a couple examples of ilmenite grains that have silica material. This one has silica and magnesium vapor deposit here on the right. And here's another ilmenite grain that has deposits of silica, aluminum, and calcium. So questions that come up when we take a look at these data, is the abundance of a specific type of vapor deposit reflective of the abundance of ferromagnesian minerals that we're seeing more of those components being mobilized and moved around to plagioclase grains? Is it something about the crystalline structure that breaks down more inherently relative to more durable phases? That's something that we would expect from mechanical rates of silicates on Earth. Do those same processes hold true on the moon? Similarly, yeah, so the sputter deposit, similarly, is that related to mechanical weathering rates of silicates? Now, these are more just kind of a gallery of cool features. We encounter throughout our analysis of the materials lots of melt features and melt blebs. These are small agglutinitic particles. They're very common, and they often contain nanophase iron and these vesicular nanophase iron, showing an example here. actually going to go across here. This is an example of texturally what we would see when we're expecting an oxidized material. So this is like a surface adhered particle of vesicular iron, and this material here is oxidized, that's coating the outside. And you can also see halos up here. And when we look at those with eels, we do see that that iron is oxidized. Now, whether that is oxidation from the moon or terrestrial oxidation, we don't know, but we can also literally see it in addition to being able to measure it with eels. These are the phases. So these melt blebs, these spherical melt blebs are typically where we also see helium-bearing vesicular nanophase iron. There's something about glass that just entrains these particles and kind of preserves the helium within them. It's very puzzling. And then finally, I want to talk about the vesicle structures that we've seen throughout the material. So when we look at the vesicles in glass, they're spherical. In all cases, I'm going to flip through too fast. These are several glass particles that just have a variety of vesicles either near the surface where we would expect in kind of a rim orientation versus throughout the whole volume of the glass particle. So the timing of when those vesicles are happening, is it a space weathering feature? Is it a feature of melting, cooling? It's a bit kind of anomalous to me at this point. In terms of vesicles and minerals, as I mentioned earlier, plagioclase doesn't really seem to form vesicles very often, but we do see them frequently or at least I see them frequently in olivine and ilmenite. And these two minerals weather rather similarly, at least from a textural perspective. They have very irregular, fracture-like, broken, sometimes linear vesicles, so to speak. So I wish I had a laser pointer. But for example, in this olivine grain here, this fracture here are vesicles, and along this grain here, they just form these fractures. And in the frozen samples, in those types of vesicles, that's where we're seeing the volatiles, the hydrogen and the helium. Ilmenite will often have vesicles that take advantage of defects in the crystal structure, so they'll be parallel to one another, and we'll often see those filled with helium. Then, all right, so that's basically all I have, but to summarize, we're using STEM, EDS, and EELS to do these comparative analyses. We don't see a clear relationship with exposure yet and space weathering features, but we're really interested to see if anyone else has at this point. We are, however, seeing trends in how different minerals experience space weathering. We've looked at hundreds of grains at this point, and kind of like going to the Galapagos and photographing finches or drawing them, I guess Darwin did. You can photograph so many and you think they're all different, but as soon as you start getting hundreds and hundreds, you start to see these trends come up. But what we see is plagioclase does seem to be resistant to weathering. We don't see vesicles or fracturing, but they are often the substrate on which we see exogenous elements being deposited. Olivine and ilmenite appear to weather similarly, at least from a textural perspective, and that deposits of the ferromagnesian elements appear more common than that of plagioclase origin elements, despite the latter having higher abundance in these soil fractions, and that we don't see evidence of the breakdown of titanium-bearing phases. And in general, we need more data on pyroxenes and accessory phases, but that's what I can say for plagioclase, olivine, and ilmenite, which are what I frequently encounter in my analysis. So that's all I have. Thank you.
Questions?
Love your EDS maps. Nice, lots of variety there. It's great. One minor point, you used the term sputter deposit, and there's a lot of wailing and gnashing of teeth about that term and that process. Do you have a basis or a thought about why you wanted to call them sputter deposits, or was that just sort of a colloquial expression? I mean, why do you call them sputter deposits?
Well, thank you for your question. I differentiate sputter deposits as being what happens when solar wind ions sputter atoms from the surface of one grain and deposit them onto the surface of another and differentiate them from vapor deposits, which are generated from impact-related vapors.
Okay.
At least that's my thinking of it. I'm certain I
Right.
could be wrong.
And I agree completely. That's the criterion. Or in any case, that's the difference in process. But what's the analytical criterion for calling something a sputter deposit in terms of composition versus a vapor deposit?
I don't have a very good, clear analytical distinction. In my mind, a sputter deposit would be something that accumulates more slowly than a vapor deposit, which I would think would accumulate a lot of material at once. And so whenever I see very thin coatings, that in my mind says that that's could be more sputtering, and also that those materials would also be more mono or polyelemental, so not just one specific phase. So if an impacted onto a grain or a collection of grains, you'd expect to see a lot of different kinds, like a mixture of elements. But the fact that we're seeing kind of pairs of elements, it kind of gives me a sense of the scale at which these materials are being moved from one grain to another. So I don't have a good criteria, but thickness is kind of what I'm going with at this point.
Great, thank you.
Good question.
Yeah, what's the relative volume abundance of vesicles versus nanophase iron?
I don't think I could.
Rough order of magnitude. Is it like, are they rare compared to nanophase iron or comparable in distribution?
I would say that I see more nanophase iron than I do vesicles in the samples that we're looking at.
But by a wide margin? I mean, we can model vesicles.
Yeah, I
so
would say
just-
I would say by a wide margin. I don't know if yeah, Kate would agree with me.
Thanks.
This is fascinating stuff. I had not seen the magnesium concentrations before, but I understand that others have. Think about is looking at the development of patinas on rocks, because those just visually in the field look like that they're related to micrometeorite impact. When you look at these little things we used to call zap pits, there's a little puddle of glass in the middle of each zap pit, and the color of that glass reflects the minerals that were impacted. And you tend to lose the patina around that puddle, but then the brownish patina basically covers all the rocks. You learn to look through it to see the mineral composition and things like that. Still, it might be useful sometime to try to look at that large rock and that patina and see if you can't make some kind of a semi-quantitative measurement between sputtering and vapor deposition. I suspected most of that on the rocks is vapor deposition, but I don't know.
Oh no, thank you. That I would love to do something like that, because the tricky part of the soils is that the grains are not next to each other where they were on the moon, and so we can't see the spread of those vapor deposits.
The Chinese have published a paper on the Chang'e 5 samples that show quite a lot of vesicles versus nanophase iron in the weathering of ilmenite. I don't know whether you've seen that one. It's a journal that I never heard of, Materials Futures. So it's one of those, one of those open access publications that are coming out of China. But they're very interested in the helium, of course. And they seem to think that space weathered materials will retain a lot of helium because of the amount of vesicles they saw. So I was intrigued by Paul's question. Something that to sort of keep in mind that there could be an important application here, but also to compare and contrast with what the Chinese saw. I can get you a copy of the paper. Well, I've got it right here. I'm looking at it, but it's something to compare with.
Yeah, thank you. No, it would be interesting to understand, and I still don't understand when we talk about grains being saturated with hydrogen and helium, what does saturated mean? Is that just interstitial atoms not finding one another and forming vesicles? How do we quantify, how do we remove that signal from the bulk? Because it's easier to detect when they're all in a nice group together. That would be interesting to know.
All right, Tony.
This is amazing work, super complicated. See if I can articulate this well. So clearly iron and magnesium are volatile relative to calcium and aluminum. I'm curious as to if you see similar differences in glass vapor deposits. Do the glass vapor deposits also, are they preferentially iron, magnesium relative to other things, or what do you see with that?
Vapor deposits on glass? They're actually kind of similar to plagioclase. Glass will also accumulate as kind of just a witness, a bystander, but the glass also have their own features. But yeah, we've observed them on glass as well. I just showed a bunch of plagioclase because I had a lot of examples of it.
I mean, it's interesting because my understanding of it is that no matter what the micrometeorite hits, it'll vaporize with sufficient energy. So presumably everything should be vaporized if it can, but you're not seeing it. And I think it's an interesting depiction of the process at play.
Yeah, I want to know where all these things are going. You think they're being vaporized, and it's strange that we're seeing more specific type of vapor than another. But another thing to remember is, and I have to constantly remind myself of this, is when we make a microtome stub and we have a few grains in epoxy and we're making these microtome slices, we are slicing through the same grain several times. So we could also be sampling just multiple examples of the same grain that's experienced the same vapor deposit. So that's another complicating factor too, which is why the fib sections are very useful to go in and pick individual grains in that way rather than getting multiple slices of the same grain.